Welcome here to this Learning Machines seminar. Today we're listening to Rami Mochaourab, working here with us at ri.se, a machine learning researcher, and he'll be talking about robust explanations for private support vector machines. Please, Rami, the floor is yours.
All right, so my name is Rami, and I'll be talking about robust explanations for private support vector machines. This is collaboration between us, at ri.se and with Stockholm University. So here, me and Sugand, we are at the Industrial Systems Division within the Industrial Systems Department within the Digital Systems Division at ri.se. And Stanley is at the Department of Law at Stockholm University, and Panos is at the Computer Science Department at Stockholm University. And this work has been done within the collaborative project Extremum within the KTH Digital Future Center. So this is a quite large project with 5 co-PIs and spanning 5 years time. And it started in 2019 as a 1-year pilot project, and it got an extension until now, 2024. So the motivation is as follows. So we see that machine learning solutions are being increasingly applied in diverse application domains, and that's mainly because of their powerfulness to learn from data, to capture essential features in the data, and to make accurate predictions. And that's very good, because we need that in many applications, to be able to do accurate predictions, fast predictions, and we save a lot while doing that. And but we're learning from data, and many times we face the concern about the privacy. In many applications, we have personal data in the data sets, and often we have this dilemma. So, do we want to use the data? We have the privacy issues, but then also, again, we have all those benefits of accurate solutions from machine learning, which are learning from those data. So this is quite a valid concern when we work with data and with analysis, machine learning analysis, to be concerned about these privacy issues. And I think this is quite important to keep in mind when we work with data. Another aspect is that the machine learning models are quite complex, and we are applying them in there are many applications where the decisions made by these algorithms is critical, and we need to make sure that these decisions are made correctly and they are valid. So these models are quite complex, and we need sort of a way to be able to understand what these models are doing. Although we have results that they are quite accurate given the data we provide to it. And here there is this branch called explainable machine learning, where we could apply certain models, not new, but I mean they're advancing, to be able to validate or to understand better these complex machine learning models. And the main motivation for using explainability here for the predictions from ML models is to first confirm, is there errors in the data that we are using? Maybe we didn't notice. So are these algorithms learning correctly from our data we're giving it? We could make errors with the data. Maybe we should have done something differently with the data. So this explainability could help identify such errors in the data. Another thing is explainability can help us understand how to influence the decisions, how to change certain inputs to the models so that we can influence the final decision. So how sensitive is the model? What is important here that can change or enhance the decisions or the outcomes? So, for instance, we get a prediction from a model, and we would like it to be different. How can we affect this. So usually in rule of thumb decisions, we know that, but these complex models have learned much more accurate predictions. So how can we do this here? So this explainability can help here. And also, again, I mean, we're learning from data. The data has, could have missed some certain parts. Could maybe the machine learning model learn something that maybe could be harmful later, at a later stage. So explainability can also help detect unfair predictions by trying to explain the predictions made by it. So these are three sort of aspects that explainability could be useful. And from this motivation, I mean, we want accuracy, we want privacy, and being able to explain the predictions by ML models. These three are indirectly or not indirectly, they are directly included in this in the GDPR, and maybe more in the law as being textual, more written, but the whole motivation of doing this work was to sort of transform these written values into a technical concept here. So how do we do that? How do we transform these values of accuracy, privacy, and explainability in a technical context? So what we did is we looked at the support vector machine classifier and learned this SVM from a data set. And then we applied a mechanism to this SVM, which guarantees differential privacy. I will talk about this in more detail in subsequent slides. And then after we guarantee that we achieve, that we guarantee differential privacy, we would like to explain the predictions made by this private support vector machine. And we analyze, or we motivate how we do that. And the relationships between all these three is as follows. So first we start with the data set. We have the data, which are privately stored somewhere. And from the data set, we learn a classifier. Here in this case is the SVM. But before publishing this classifier for use, for public use, we need to guarantee that it does not, there would be no breaches in privacy in this case. So before publishing this, we need to apply a privacy mechanism. And once we do that, and we guarantee this notion of privacy, we publish the classifier. And this is publicly released. And now we would like to explain the predictions made by these, by this model. And here we would look at the sort of explanations that are robust to the uncertainties introduced by this privacy mechanism. And this is exactly also the outline of the talk. So I will start with the data set and SVM learning. Then we will look at the privacy mechanism and like show the privacy mechanism for SVM called private SVM. And then we will look at the characteristics of this mechanism and define counterfactual explanations and try to solve the robust explanation problem. And we will go to the few experiments. So let's start here with the data set and SVM learning. So we have a data set, collection of n tuples. So we have n rows in a database. And let's say each row corresponds to a person. And each row has the columns corresponding to those attributes of that particular person. And the attributes here, we assume we have an L-dimensional vector of features, in this case X. And we assume that we have two classes of cases in this data set corresponding to -1 and 1. And that would be the label for each feature here, xi. And the task here is to learn a function from the data set. So we learn from this data set a function that would accurately separate these two classes of points. And for the support vector machine case, here we have an illustration. So looking at the left-hand side here, The red points would be, let's say, the -1 class, and the green points would be the +1 class. And we search for a linear classifier here in this case to characterize this boundary that would separate the two clusters of points. And then in this case here on this side, we have the separable case. So the boundary perfectly separates these 2 points. But I mean, you could draw any boundary here like this or like this or like this. The support vector machine finds this boundary, which is most robust in the sense that it maximizes the margin between the points. So the support vector machine draws this line where this distance between here and this line passing through the first point it touches, and this line is maximized. And in that sense, it's generalizable. It generalizes to other points in the best way it can, given this test data points. Now, in the case where the points are not perfectly separable, this is the soft margin case, we just include some penalty when each point passes to the other side. And this is also handled similarly by just including some penalty terms for these. So formally, the support vector machine optimization looks as such, where we have a minimization of 2 terms here, 2 objectives, let's say. And this term here on the left has a parameter C, which is fixed. This is a free parameter one can fix. And here's the total number of points in the data set. And this term here quantifies the misclassification on the test data. And this needs to be minimized. And then again, here on this side, we have a sort of regularization term, which we typically have to make things more nicer. So this is the typical formulation. It's a convex problem. We can solve for these weights W, which are the optimization variables here. So now we learn, let's say we optimize this, and we learn the optimal classifier weights. The next step is to use the classifier based on that. But before publishing these weights, we need to guarantee that there would be no privacy breaches occurring here, and we need to apply a privacy mechanism. So, so before going in detail about how to sort of manipulate the information at this stage before publishing, I will talk a bit about differential privacy. One slide. So the goal of differential privacy is to protect each individual in the database while still allowing to perform statistical analysis. So still allowing that the data set is useful for something. And how it's done, it's by ensuring that the responses for from querying the database are equally, the responses are almost equal, given that one individual or any individual is in the data set or not. So this is what it ensures. So in a certain sense that we're querying the database, and if an entry is there or not there, the querying would be equally likely. And how is this achieved? Through introducing randomness in the responses. So we introduce randomization, and we introduce uncertainty about that. So, and the formal definition now for differential privacy is as such. It's a bit technical. So it starts with the definition of a randomized mechanism, M, which takes as input a database and outputs a response from the database. And this would be the response we are interested in. And this mechanism, this randomized mechanism, provides beta differential privacy, where beta here is a parameter which we set by hand. If we take all possible pairs of data sets that differ by only one entry, one row in the data set, if we take all of those pairs and we take all possible responses from this mechanism M, then this condition holds. And what this condition says is what is written here. It ensures that the response would not change much, would change very little if one entry in the database is not there. And what's important to note here is that the privacy is parameterized by this parameter beta, and the smaller beta is the higher the privacy. And this is quite like a tunable notion here, or condition here. So this notion of privacy, differential privacy, has been applied to SVM learning in this paper here, Rubinstein, and they characterize a mechanism to guarantee differential privacy. And this mechanism, what it does, it adds IID Laplacian noise to the optimal weight vectors before releasing these weights to the public. And these weight vectors, they are IID Laplacian, and the elements of this vector, IID Laplacian, and with zero mean and scale lambda. And the important question is how to relate this lambda to the beta of the differential privacy. And they have several results here. One of them is what we use here, and it is a lower bound on this lambda. This is you can imagine it as the variance of this noise. So a lower bound on this scale lambda is given by this here, this term. And this term consists of those fixed terms. C is the SVM parameter. And the kappa here should satisfy that this product is less than kappa squared. So this is the feature mapping. So if you imagine that we have a linear SVM, so it would be like x times x for all data points in the domain of the data should satisfy that they are less than this kappa. So kappa here sort of gives information about the data points in the data set. F is the feature space dimension, and N is the number of points in the data set. And you can see sort of the lower bound scales inversely proportional to the number of entries in the data set. If we have larger number of points, we get a lower bound, and in that sense, we could reduce the noise, because then having more entries in the data set improves the privacy. This is what it's saying for a fixed beta. So this is the mechanism proposed in this paper, and now after perturbing those optimal weights, we have this W tilde, and these are publicly released. And this mechanism should provide better differential privacy. Now we are at this stage, and the next step would be, now we have this private classifier, and we want to explain predictions made by this classifier. And we select a specific model called counterfactual explanations to explain the predictions by the private SVM. I'll talk a little bit about counterfactual explanations. So it's one class of explainability methods that quantify the necessary changes to a particular data point, data instance, in order to alter its prediction to another desired prediction. So what does it include? So the things here, we have a classifier, let's say, and we have an instance, one single instance given, and we have from this data point, we want to understand the prediction given by that classifier. So here, the values for each feature of this data point cause that specific prediction from the classifier. So let's say we have here this x vector, and x1 or the x2, x3, xl are the elements of this vector, and those specific values, they lead to the prediction by the support vector machine. And counterfactual explanation, this model, it quantifies how much should we change each of those values so that the prediction changes to something we want. So and preferably we want the smallest changes in these values to achieve that alternative prediction. Now this is the model of counterfactual explanation. In a mathematical way to write that is as follows here. So we have an SVM classifier with a weight vector W, and a counterfactual explanation for a classification y prime of a given data instance. This is the point I have, and this is y prime is the classification of that point by that classifier. And now the explanation for it is the solution of this problem. We want to find a point which is closest to x prime. So d here is a distance metric. So the point which is closest to that point, but the constraint is this here, which says that the class of that explanation should be different than x prime. And this, so here in our case, we have two classes, +1, -1. And if we want to change the class, this constraint would express that. So if this is +1 and this is -1, then it's satisfied. If this is +1 and +1, this will be violated. -1, -1, this will be violated. So again, here, the objective is to find an explanation which is closest to x prime. Constraint, the explanation, the counterfactual explanation should have a different class than x prime. And the problem here is that the private SVM has noisy versions of those optimal weights. And due to that, the problem is the constraint would be, due to those perturbations of those weights, the constraint here would be violated very often compared to the unknown optimal classifier. And this would mean that if we just use the private SVM classifier and we explain a specific point, let's say with a classification -1, and we just have a noisy version of that classifier, then the explanation could be of class -1 also. So that means if we have a diagnosis and we're telling that person, you have this diagnosis, and I want an example of another diagnosis, I would give that person the same diagnosis because it's a private classifier. So we would need something that is more robust to those uncertain, to those noises in the private SVM. And this is the sort of the main problem or issue we want to study here. And what we do is we model this uncertainty about the unknown optimal weights of the support vector machine through a random vector, here zeta, xi. And it's modeled as such. So we have the W tilde, the private SVM weights, minus this random vector where the elements of mu here are IID Laplace random variables with 0 mean and scale lambda. And instead of using this model for counterfactual explanation, we use in the constraint here a probabilistic constraint, which is written here. We minimize the distance between the points while the probability that this constraint is satisfied is larger than P. P here is the confidence level value between 0.5 and 1. And this problem we prove is equivalent to this here. So we find the deterministic equivalent for this probabilistic constraint as such. So we use the characteristics of this random vector here to derive that. And I will use later this function g, which is exactly this left-hand side of this. Now, we did that, and now we want to find the counterfactual explanations. So it turns out for the general SVM, we have here this phi, which is the feature mapping. which is typically used in SVM to sort of enlarge the feature space in a way that the points will be better separated by a linear classifier. Now, in the case where we have a linear SVM, this phi of x would be equal to x, so we don't have a feature mapping. The problem is convex. It corresponds to a second order cone program, and we can solve it efficiently. And we have here the linear case. So for a two-dimensional data set, these are just two Gaussians with the means here and here. We have two classes of points, the green and the gray ones. We have here the dimension 1, dimension 2. And
Rami?
Yes.
I think maybe your slides have stuck.
Which slide do you
I'm
see?
seeing the proposition, slide 9.
Okay, I'm on slide 10. It happened before. Shall I restart the sharing?
Try that.
Maybe it helps. Now?
Now
Do you see?
I'm seeing the black screen again.
Okay. Let me try the. Okay.
Let me know if anyone else sees anything better.
I'll try another option of sharing. Now?
It's still black.
Oh, okay.
I am assuming that it's the same for other viewers.
Okay. Let me re-enter. Restart Zoom.
It's black for others as well.
Like yes. Here too. Oh, okay. So from my side. Okay, I will restart Zoom. I'll be right in.
Yes. There seemed to be an issue with Rami's computer.
Okay, yes. now I'm sharing. You
it's
see,
better.
Where is it? Slide 10. You
yes.
see? Oh, great. Okay. So here we are with the linear SVM case. And for this case, it's a convex problem. The counterfactual explanation, robust counterfactual explanation problem is an SOCP. And here's one illustration for two-dimensional data set where here we have x1 and x2, and we want to illustrate like what on this case, what does robustness mean here? So the black line here is the optimal SVM or non-private SVM here, and the perturbed version is this dashed line. Now we have this instance, the black dot here, and we want to explain it using counterfactual explanation. And because we want this to find the nearest point to that point, but of the different class, of course, that point would be the point which is perpendicular. Would be that point which is the closest to it, where we're using the Euclidean distance here. So as you can see, the explanation is on the wrong side compared to the optimal classifier. So we are explaining this point by another point with the same class, and this is not so desirable. While in the optimal case, if we know the optimal classifier, the non-private one, the explanation would be that square here. So if you draw the perpendicular, that would be this point. Now for the robust explanation, if we solve this problem, we get to this red point. Now it's not on this line, of course, but it is robust in the sense that it gives some distance to make the confidence that the constraint is violated quite low. And this is specified by, we can specify it. I think in this case it was 0.9. The P here was 0.9. So we get a point, knowing only this boundary, and get a point that this satisfies the constraint 90% of the time. And this is what we want to achieve, that the explanation is, okay, as close as possible, but not as, in this case, of course, but it doesn't violate the constraint for the boundary, which we don't know. This can be seen nicely with the linear SVM, but linear SVM, of course, is not always so accurate. If we look at SVMs where we have a feature mapping corresponding to some kernel, the problem here is not convex. So then we need to look at suboptimal solutions. And the approach here is to if we look at the problem here, and we have this function g, we see that actually if we find a root for this function where this equals to 0, this would be a good counterfactual explanation. So as you can see here, the explanation is on the boundary in the sense that g of x here will be 0 because it's directly on the boundary. Well, g of x will be here +1 and here -1. And if it's on the boundary, it will have value 0. So the problem is a root finding problem for this function g. And what we do is we apply the bisection method to find a root for g. And this is a suboptimal solution, but it's quite efficient to do. For the experiments, we used one data set, the UCI breast cancer Wisconsin data set, includes 569 instances and 30 features for each data point. And we have a binary classification problem between benign or malignant. We split the data into training and test data sets, 70-30. And we used an approximation for the radial basis function from this paper here. And we use the Euclidean norm as distance function. So first we look at the accuracy privacy trade-off, compare the private SVM and the non-private SVM. On the x-axis, we have beta for the beta differential privacy. The smaller the beta, the more privacy, but at the cost of more noise to the classifier, which leads to less accuracy. But when we increase beta, we have improved accuracy. So this is intuitive. So one example of counterfactual explanation for this data set. So we picked one instance and we calculated the counterfactual explanation and did some normalization. Here on the x-axis are the features. We have 30 features. And for that example, we saw that feature 19 needs to, so this instance is classified as malignant. And what do we need to change in the features to change the classification to benign? And we see that most of the features need to reduce by half their amount, like these, and one feature 19 needs to increase by half its amount. So this is the type of explanation given by counterfactual explanation. Now it doesn't say much to me, but I think maybe the doctor can understand the result here. Now we look at the average distance between the instance we want to explain and the explanation. So this was the objective in the counterfactual explanation, to have the smallest distance. On the x-axis, we have this confidence level within the probabilistic constraint. Now, if we have very low confidence level at 0.5, we converge to the non-robust explanation for private SVM, and that's the same as the as if we knew the optimal values for the weight vectors, because we have zero mean noise here, so the fluctuations will be around the decision boundary. So here at very low confidence level, the distance is the smallest. But if we want to have more confidence that the classification of the counterfactual explanation is on the right side, we need to increase P. And as we increase the confidence level that the constraint is satisfied, we sacrifice the distance to that point. But that, I mean, that we need to have the constraint satisfied. And eventually we converge to what we used as prototype for the bisection method, which is sort of the mean of the data points, if we take the cluster mean in this case. And this is something necessary for the bisection method, where we could assume just we randomly sample the space until we get that point, the prototype, or that the domain expert has at least some intuition what the values should be to start the bisection method here. So this sort of shows, okay, we need the confidence here that we don't violate the constraint, but then here at the expense of the distance to that point. As a conclusion, we have studied counterfactual explanations, robot counterfactual explanations for private SVM. So here we have differential privacy introduces randomization, introduces like the uncertainties about the responses. And we showed that this affects the quality of the counterfactual explanations. And what we proposed are robust explanations which depend on the level of privacy and the level of confidence for satisfying this counterfactual explanation constraint. That is my last slide. We have the preprint, and the code is available on GitHub if you're interested in reproducing. So thank you.
Thank you, Rami. Do we have any questions for the speaker today?
So this is Misha. Olof, may I?
Yes.
So I understand. Hello, Rami. It's been
Hi,
a while.
Misha.
You've been in the office, so. So yes, so the counterfactual explanation exists for each data point, right?
Yes, it targets each instance you select. So yeah, not the model.
Vector. Each vector, each data vector you have with the answer.
Yes.
-1 applies 1. Already we've applied the differential privacy. Okay, good. The thing is that it's very nice that for each data point, you kind of can manipulate the input parameters so it changes the value. But there must be many ways to do that, not only one. Am I correct?
Yes, you want to find the smallest distance, the smallest changes in a certain metric, or in a certain sense of distance.
The smallest, and it means that, but the smallest, that means with respect of the parameter of interest, or no, it's of the sum metrics along all parameters, right?
So for example, if D here is the Euclidean norm, you would find the here is this nice it shows it nicely that you would want to find if you draw the perpendicular to that line, you would find the point on that line which is closest to this point, and this is what you're searching for.
Yes, but it means that it's a kind of according to some metrics which take into account all the parameters, because that would be interesting. Because in this application context, it means that the doctor can see at least one case where this prognosis can swap. But for this specific patient. But the interesting thing that there can be other variations, not the minimal one, but
okay, yes, I understand. So there are some, for example, that it could be that this point is not of interest because it's outside the data domain for the doctor. Let's say, for example, what if some features you cannot change? Let's say one feature is, for example, if the data is an apartment, let's say, and one feature changes the size of the apartment, it's something that you cannot change. That could not be a solution for counterfactual. You would need sort of what are the parameters that are changeable. Let's say maybe if you can invest like a new kitchen, or I don't know, like allowing maybe changes only in the parameters which are really actionable parameters.
Yeah. But then the explanations also depend a lot on the fact that we have a linear decision boundary and on this distance metric of choice.
Right.
Because as a doctor, I mean, if we get back to that example, I would really like to have a set of options, like the most probable, the easiest one, the next easiest one, the third easiest one, which kind of change the prognosis, you know, not only one, but a few of them for each specific patient. Because the good thing that we can pick up of each specific patient and say, oh, look, but you have a positive prognosis now, but if you swap this and that, you get the negative prognosis. But that's only one scenario. It can be many, because you can have other combinations of reducing and increasing parameters.
I think it sounds like we're talking about the complexity of the learning model. And if we have a linear SVM, then that's a limitation. Of course, if we have a kernel-based SVM, it's more expressive. And also it's no longer convex, right? So exactly. You could find these would be different local minimas, I would assume, in this optimization, in this searching of the counterfactual. Is that the correct intuition, Rami?
Right, you're right. Yes. So in this case, you would have several routes, and you would converge to one of them. It would be like a local minimum there, or so in this case here, we would have several routes, and we would converge to one of them, not necessarily not always the closest, for example. This would depend on so the bisection method takes this function, and we start. Let me show it here. So the bisection, we start with 2 points, one the instance and the other point somewhere here, and we just have the spaces between them iteratively until we converge to a point where the function is 0. Now, if there's several zeros, we could converge to another 0, which could be not the one necessarily closest to this one. So it is challenging in this non-convex case. And also, I mean, generally, if we consider different types of kernels, it's very difficult to work with kernels. So yeah, analytically here in this case, but for the bisection method. But the nice thing, I think you noticed that, I mean, the approximation, I've used an approximation here, this phi through this paper, for which directly could show the. So usually the kernels take as input 2 points, so they map from. So yeah, maybe it's too complex to describe it without some math. But anyway, here's just the feature mapping, which is an approximation for that, and it could nicely like show but I mean, if you plot it, you will see that it's challenging. Of course, you will get like dots, and the boundaries are quite difficult to handle. But I think, Misha, you mentioned, I felt that you would want a better quality counterfactual explanation that is, in the sense that it includes some like desirable aspects which the doctor would want, not necessarily just that it's on the closest and with the different class, but maybe it satisfies some other things. But these, I think, could be included in the optimization, whatever you would like, as long as you can keep it convex. Everything is sort of
safe.
I
mean, if I look from another perspective and forget about SVM for a second, so if as a doctor, if I am, say, I would like to know what changes, like first the minimal one will lead to switching the prognosis. But we can assume there might be the second closest, when we choose another combination of parameters, it swaps, there is another swap, it's the same in the same direction. It's like goes, for example, from positive prognosis to negative. But I would like as a doctor to have not one, but a few possible scenarios, 3, 5. So then based on that, I will be able to give recommendations for the patient what not to do, for example, so that the prognosis, or another way around, if the prognosis is, for example, negative, just what you need to change that the prognosis will be positive. This is where the value is.
Stop smoking or start medication.
Yeah.
But we can't give so much options to the patient. It's like, you cannot not stop smoking. You should stop.
Yeah, but so you say you start smoking. They say, no, this is not an option. So okay, we try something else.
Give me the second best.
Yeah, give me the second best. Yeah.
Exactly.
Do we have some more questions? I'm thinking a bit about the factors and the hyperparameters and the beta and the kappa and the c, and how do all these affect the final in practice and in the experiments that you have seen? How good is the privacy, and how good are the explanations, and how do they relate to all these to more or less this expression with a lambda? That's a long and complex question.
Yeah. So the thing is, the paper is. I've used a small part of the paper, but my aim was to go to the. So there is, as you saw here, we're using the approximation with the feature mapping, and there's also so the let me remember. So yeah, okay, I will not go there. So this is the case where we are not dealing with the approximation of the feature mapping, and this is quite simple. But let's stay here. The problem is that if we want to enlarge the feature space using these feature mappings, we usually go very large, like 1,000 or something. And we would get better results once we enlarge the feature space. So you see the f here, which scales with square root f. This is a problem because this enlarges the lower bound. And I faced this problem. So I used 100 in the end. But this is one issue when you're dealing with this enlarged feature space, which will lead to better accuracy. So this is one issue. The other issue, of course, if the data set has not so many points, I mean, if you have a large data set, that's good, because then you don't need to perturb so much. But in our case, we had 500 something. Also C, that's also an important point. With the C here, this paper does not use an intercept. So everything is, how is it? No. So the optimization is quite different than, so yes, so the C here scales as square root n. And it's not typically as 1 or normalized. As you saw in the optimization, it is C over n, and usually you have just a C. So this C, they say it should scale as square root n, and this is a problem here. I mean, the problem is once this lower bound gets bigger. So in the end, after reading this paper, yeah, maybe I felt that the bounds are quite like restrictive, and you need to try many things to get into like the optimal situation. So this is increasing with n. So we have n here, and then how to choose the beta is also quite challenging, because it's not easy to say, okay, what beta I would choose, how to relate it to privacy. So so just looking at the trade-off between accuracy and privacy. Of course, in general, when papers work with the differential privacy mechanisms, they look simultaneously also at the accuracy. or the usability of the algorithm at the end. So it's not, I mean, if you want to achieve privacy, you can add noise as much as you want, but you cannot just do that. You need to, at the same time, put an upper bound on lambda. And there are bounds, upper bounds on the lambda here too, where they define here in this paper something called usefulness of the mechanism. And it gives an upper bound on this. And so one has to stay within these limits with the lambda. I have a lot of code on this also from this here, and I plotted like all the parameters, how they bound each other. So it's quite interesting. But I felt that not so much work extended it to more like better bounds. I felt that the proofs were quite loose somehow. I felt that. And they write also in the discussion at the end that there could be much improvement also. So yeah, but many parameters. Yeah, sorry.
I think a lot of intuition came with, I think, the last plot you showed, where you showed the distance to the counterfactual example as a function of p. I think
this one.
Yes. And I mean, you pretty soon go p. I mean. If you invert it, you can say that p grows fast in the beginning, while the distance is between 3 and 4. For example, we go up to p equals 0.7 or something. But then not so much, and then the distance sort of grows, and once you're at the prototypes, I suppose the explanations aren't that informative anymore. Once you get to
they're far away. Yeah, once you get further away from the point you want to explain, you lose the relationships a little bit. This is the concern. Yeah, exactly. Yeah. I have also plots for where we have the beta here, and those plots show what we are targeting. And I could show those in the back. So if you look at this plot here, it's again the average distance to the point we want to explain. Here we have beta while we fix p to 0.9. So for beta very small, we have higher privacy, and here we have higher distance with the robust explanation, the red curve here. The non-robust explanations, they fluctuate around the boundary, so the distance stays on average, like as in the non-private SVM explanations. Now, this shows that how the curve changes with beta. Now we have a drop or the distances are bigger, but if we want to look at the constraints more specifically, I've plotted here these two. So the left-hand side looks at the violation of the constraint for the non-robust explanation. So that's the blue curve here. How much do we violate the constraint? And for the non-robust case, and I plotted the percentiles here for the constraint. So this constraint here should be less than 0. And we see that here we have the 90th, 95th, and 99th percentile, and the mean is around 0. The mean, we get this distance here. But if we look at the robust case, we have this shift down. So we satisfy the constraint. Here in this case, it's 90% of the time. So it's exactly as we specify with this. So it's a sort of like validating. And this shows sort of, yeah, well, that we're achieving this guarantees here, but losing here. I mean, there are thoughts of, yeah, it's not necessarily, it should not necessarily always be the case that if we guarantee more privacy, we should get degradation and explanations. We're looking into that and other work in this project to simultaneously enhance privacy and explanations in a certain way. But we'll see if we get good thoughts or results there. So, but here we see that there's some degradation due to privacy. Degradation and explainability due to privacy.
Thank you, Rami. And everybody, welcome back next week. We'll have a visitor from Lund University, Alexis Pirinen. We'll talk about policy-based reinforcement learning and applications in computer vision. So, 22nd of April. Thank you for today.
Thank you.
Thanks.
Bye-bye.
Thanks. Bye.
Bye-bye.
Thank you. Bye-bye.